Firefighting foam is a foam used for fire suppression. Its role is to cool the fire and to coat the fuel, preventing its contact with oxygen, resulting in suppression of the combustion. Firefighting foam was invented by the Russian engineer and chemist Aleksandr Loran in 1902. The surfactants used must produce foam in concentration of less than 1%. Other components of fire-retardant foams are organic solvents, foam stabilizers and corrosion inhibitors. Overview. Low-expansion foams such as AFFF have an expansion rate less than 20 times a low viscosity, mobile, and can quickly cover large areas. Medium expansion foams have an expansion ratio of 20 to 100. Higher expansion foams have an expansion ratio over 200-1000 and are suitable for enclosed spaces such as hangars where quick filling is needed. Alcohol-resistant foams contain a polymer that forms a protective layer between the burning surface and the foam, preventing foam breakdown by alcohols in the burning fuel. Alcohol-resistant foams are used in fighting fires of fuels containing oxygenates, e.g., MTBE, or fires of liquids based on containing polar solvents. Class A foams. Class A foams were developed in mid-1980s for fighting wildfires. Class A foams lower the surface tension of the water, which assists in the wetting and saturation of Class A fuels with water. This aids fire suppression and can prevent reignition. Favorable experiences led to its acceptance for fighting other types of Class A fires, including structure fires. Class B foams. Class B foams are designed for Class B fires, flammable liquids. The use of Class A foam on a Class B fire may yield unexpected results, as Class A foams are not designed to contain the explosive vapors produced by flammable liquids. Class B foams have two major subtypes. Synthetic foams. Synthetic foams are based on synthetic surfactants. They provide better flow and spreading over the surface of hydrocarbon-based liquids, fast knockdown of flames. They have limited post-fire security and are toxic groundwater contaminants. Aqueous film-forming foams are water-based and frequently contain hydrocarbon-based surfactants such as sodium alkyl sulfate and fluorosurfactant, such as fluorotelomeres, perfluorooctanoic acid, or perfluorooctanosulfonic acid. Alcohol-resistant aqueous film-forming foams are foams resistant to the action of alcohols and can form a protective film. Protein foams. Protein foams contain natural proteins as the foaming agents. Unlike synthetic foams, protein foams are biodegradable. They flow and spread slower, but provide a foam blanket that is more heat-resistant and more durable. Protein foams include regular protein foam, fluoroprotein foam, film-forming fluoroprotein, alcohol-resistant fluoroprotein foam, and alcohol-resistant film-forming fluoroprotein. Protein foam from non-animal sources is preferred because of the possible threats of biological contaminants like prions. Applications. Every type of foam has its application. Higher expansion foams are used when an enclosed space, such as a basement or hangar, must be quickly filled. Low expansion foams are used on burning spills. AFFF is best for spills of jet fuels. FFFP is better for cases where the burning fuel can form deeper pools. And RAFFF is suitable for burning alcohols. The most flexibility is achieved by RAFFF or RFFFP. RAFFF must be used in areas where gasolines are blended with oxygenates, since the alcohols prevent the formation of the film between the FFFP foam and the gasoline, breaking down the foam, rendering the FFFP foam virtually useless. History of firefighting foams. Water has long been a universal agent for suppressing fires, but is not best in all cases. For example, water is typically ineffective on an oil fire and can be dangerous. Firefighting foams were a positive development in extinguishing oil fires. In 1902, a method of extinguishing flammable liquid fires by blanketing them with foam was introduced by the Russian engineer and chemist Aleksandr Loran. Loran was a teacher in a school in Baku, which was the main center of the Russian oil industry at the time. Impressed by the large, difficult-to-extinguish oil fires that he had seen there, Loran tried to find a liquid substance that could deal effectively with the problem. So he invented firefighting foam, which was successfully tested in several experiments in 1902 and 1903. In 1904, Loran patented his invention and developed the first foam extinguisher the same year. The original foam was a mixture of two powders and water produced in a foam generator. It was called chemical foam because of the chemical action to create it. In general, the powders used were sodium bicarbonate and aluminium sulfate, with small amounts of saponin or licorice added to stabilize the bubbles. Handheld foam extinguishers used the same two chemicals in solution. To actuate the extinguisher, a seal was broken and the unit inverted, allowing the liquids to mix and react. Chemical foam is a stable solution of small bubbles containing carbon dioxide with lower density than oil or water, and exhibits persistence for covering flat surfaces. Because it is lighter than the burning liquid, it flows freely over the liquid surface and extinguishes the fire by smothering action. Chemical foam is considered obsolete today because of the many containers of powder required, even for small fires. In the 1940s, Percy Lavin Julian developed an improved type of foam called aerofoam. Using mechanical action, a liquid protein-based concentrate, made from soy protein, was mixed with water in either a proportioner or an aerating nozzle to form air bubbles with the free-flowing action. Its expansion ratio and ease of handling made it popular. Protein foam is easily contaminated by some flammable liquids, so care should be used so that the foam is applied only above the burning liquid. Protein foam has slow knockdown characteristics, but it is economical for post-fire security. In the early 1950s, high expansion foam was conceived by Herbert Eisner in England at the Safety in Mines Research Establishment to fight coal mine fires. Will B. Jameson, a Pennsylvania mining engineer, read about the proposed foam in 1952, requested more information about the idea, and proceeded to work with the U.S. Bureau of Mines on the idea, testing 400 formulas until a suitable compound was found. In 1964, Walter Kidd and Amp Company bought the patents for high-expansion foam. In the 1960s, National Foam, Inc. developed fluoroprotein foam. Its active agent is a fluorinated surfactant that provides an oil-rejecting property to prevent contamination. In general, it is better than protein foam because its longer blanket life provides better safety when entry is required for rescue. Fluoroprotein foam has fast knockdown characteristics and it can also be used together with dry chemicals that destroy protein foam. In the mid-1960s, the United States Navy developed aqueous film-forming foam. This synthetic foam has a low viscosity and spreads rapidly across the surface of most hydrocarbon fuels. A water film forms beneath the foam, which cools the liquid fuel, which stops the formation of flammable vapors. This provides dramatic fire knockdown, an important factor in crash rescue firefighting. In the early 1970s, National Foam, Inc. invented alcohol-resistant AFFF technology. RAFFF is a synthetic foam developed for both hydrocarbon and polar solvent materials. Polar solvents are combustible liquids that destroy conventional firefighting foam. These solvents extract the water contained in the foam, breaking down the foam blanket. Therefore, these fuels require an alcohol or polar solvent-resistant foam. Alcohol-resistant foam must be bounced off of a surface and allowed to flow down and over the liquid to form its membrane, compared to standard AFFF that can be sprayed directly onto the fire. In 1993, Castrine of Rome, New York, developed a wetting agent with superior cooling properties that is effective on Class A, Class B, Class D as well as pressurized and three-dimensional fires involving both hydrocarbon-based fuels and polar solvents such as alcohol and ethanol. This wetting agent, classified as a firefighting foam, was first marketed under the name of Pyrocool. The patented formula was awarded the 1998 Presidential Green Chemistry Award as a biodegradable alternative to AFFF and RAFFF and other foams and wetting agents. It is now marketed under the name NovaCool UEF. NovaCool UEF is applied at 0.4% for Class A fires and 0.5% for Class B and Class D fires. NovaCool UEF is biodegradable. In 2010, Orchidée International of France developed the first FFHPF, the highest performing fluorine-free foam. The foam has achieved a 97% degradability rating and is currently marketed by Orchidée International under the brand name Lufoam. The foam is used at 3% both on hydrocarbon and polar solvent fires. Health concerns. Studies have shown that PFOS is a persistent bioaccumulative and toxic pollutant. It was added to Annex B of the Stockholm Convention on Persistent Organic Pollutants in May 2009. Regulations in the United States, Canada, European Union, Australia and Japan have banned the new production of PFOS-based products, including firefighting foams. 3M phased out production of PFOS in 2002 over toxicity concerns. One study, published in 2015, found that firefighters were more likely to have fluorinated surfactants in the bloodstream. In 2016, the U.S. Air Force paid $4.3 million for a water treatment system for residents downstream of Peterson Air Force Base.